All right, so we'll take a look at some of the ALEKS topics for this week. And the first one here in the stoichiometry module is using a chemical equation to find moles of product from moles of reactant. So when it comes to anything involving stoichiometry, probably the most important thing that you need to do is you need to make sure that you have a chemical equation that represents the reaction in question, and then you also need to make sure that that equation is balanced properly. So in the last week, you had some practice balancing equations. Now we're going to use those balanced equations to solve these stoichiometry problems. And this really is probably the most challenging part of questions like these, because they don't actually give you the equation, but they tell you what the reactants are and they tell you what the products are. So you have to look into what they give you here in the question. So it tells you ethanol reacts with oxygen. So we have the formula for ethanol, so CH3, CH2OH, that reacts with, so use a plus sign, oxygen is O2, and then it says to form water, so that means it produces, we have our arrow, water is H2O, and then we also have aqueous acetic acid, and then it's given that formula CH3COOH. So that's your equation that represents the reaction in this question. We want to make sure that it is balanced. So we're going to insert coefficients wherever we need them to make sure that we have the same number and types of atoms on the left side, on the right side. So we have a bunch of carbons, we have some H's, and we have some O's. So on the left side, we have 2 carbons. On the right side, we have 2 carbons. On the left side, we have 3, 4, 5, 6 H's. On the right side, we have 3, 4, 5, 6 H's on the right. On the left side, we have 2 O's and another O, that's 3 O's. And then on the right side, we have 1 O plus 2 others gives 3. So this actually is a balanced equation already. In this case, we need to balance it. And then remember, when you don't see a coefficient, 1 is understood to be here. Okay, so those coefficients are important because they give you a mole-to-mole ratio in any of these equations. So the coefficients, which are these things that we insert to balance the equation, give a mole-to-mole ratio. And you can think of that mole-to-mole ratio as an equality or as a conversion factor if we need to use it as such, to solve this problem. So for example, now it's telling us calculate the moles of acetic acid, that's this thing, produced by the reaction of 1.40 moles of ethanol. Ethanol is this thing, right? So what we're trying to relate now that we have our balanced equation, is we are trying to relate the ethanol to the acetic acid. And the relationship between them is, or are the coefficients in the balanced equation. We're trying to relate the CH3, CH2OH to the CH3, COOH, and we use there the mole-to-mole ratio, which in this case is just a 1-to-1 mole ratio. So we can say then, according to that ratio that we get from the balanced equation, that 1 mole of the ethanol, CH3, CH2OH, produces or equals 1 mole of the acetic acid, CH3COOH. That is an equality, and we've seen equalities over and over and over again in this class. The good thing about equalities is that we can turn them into conversion factors simply by putting one side over the other side of the equality. This is just another way where equalities can be generated, is by using the coefficients from the balanced equation. So we have our first conversion factor. The second one, we simply flip it. All right, so we have 1 mole of CH3 COOH for every 1 mole of the ethanol, CH3 CH2OH. So now we have, from the balanced equation, we have a mole-to-mole ratio that we express as an equality that we then can convert into one of 2 conversion factors. Now we can go ahead and use the information that's given. So it says that we want to figure out, we need the moles of ethanol, I'm sorry, the moles of acetic acid, which is a CH3COOH, that's produced from starting with 1.40 moles of the ethanol, CH3CH2OH. Okay, so in order to go from moles of the ethanol into the moles of the acetic acid, we need the relationship or something that relates those two things. We're going to use one of our two conversion factors up here. Since I want to end up with moles of acetic acid, I'm going to choose a conversion factor that has acetic acid on top. That's the one on the right. And I'm going to set that up. So I'm going to start with what's given, my 1.40 moles of CH3CH2OH, put that over 1, and then take that conversion factor and stick it right here, keeping track of the units. So 1 mole of the acetic acid goes on top. For every 1 mole of the ethanol that goes on the bottom, moles of ethanol go away, and you can probably see that in a 1-to-1 mole ratio, if you start off with a certain number of moles of one thing, we'll have the same number of moles of that other thing at the end. So we should get 1.40 moles of the acetic acid. All right, so now we're going to take a look at identifying the limiting reactant in a drawing of a mixture. So here it's they're provided with a sort of a model of a reaction that's occurring. Okay, so it tells you, in this case, you have a mixture of molecules to start off with. These things are color-coded, so the sulfur is in yellow, and then the oxygen is in red. And the reaction that is going to occur here is the SO2, which are going to be these things. Those are the SO2, 1 sulfur and 2 oxygens linked together, sulfur dioxide. They react with the oxygens, so which is the O2, 2 O's, 2 red spheres linked together, to make SO3, sulfur trioxide, sulfur, and 3 O's. So here it's asking you of which reactant, so that's either the SO2 or the O2, are they the most initial mole. So in here, you can think of the number of molecules as being directly proportional to the number of moles. So which one do we have more of, the SO2 or the O2? Well, just by looking at it, as you can see, we have 1, 2, 3 O2s, right? 1, 2, 3. And then we have SO2s. Let's see, how many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 SO2. So the greater initial moles would be the SO2. The least initial moles will obviously be the O2, right, where we only have 3. And then it asks, which reactant is the limiting reactant? So the limiting reactant is the reactant. So one of the things that we're starting with that is used up first. So because it's used up, if there's none of it left over at the end, it limits or it stops the reaction from going any further. There's none left at the end. So if we take a look at our equation and the number of each of the reactants that we're starting with, so the balanced chemical equation says that 2SO2 reacts with 1O2. I'm going to put the 1 in here to produce 2 SO3s. Okay, so the way that we can approach any limiting reactant problem is to start with and do 2 sets of calculations. We start with each of the reactants. So we're going to say starting with the SO2, and we have 8 moles of the SO2. So we can say 8. We'll just use SO2 for right now. And according to our chemical equation, 2 moles of SO2 produces 2 moles of SO3, right? So that's our mole to mole ratio. We can say 2 moles of SO2 produces 2 moles of SO3. Obviously here, the SO2 cancels out, 2 cancels out here, we get 1-to-1 ratio. This gives the same number, 8 moles of SO3. So if I used up all of the SO2, I should get 8 moles of the SO3. I'm going to do the same thing now with just the O2. Okay, so I have, how many O2s do I have? 3 O2s. So I have 3 O2. And from the balanced chemical equation, I now relate the O2 to the SO3, right? The reactant to the product. So it says that for every 1 mole of O2, I produce 2 moles of SO3. I'm just going to put 2 SO3 for right now. So 2 SO3. Okay, so the O2 goes away, and I multiply out. 3 times 2 is 6, divided by 1 gives me 6 SO3. So if I use up all of the O2, I'm going to get 6 SO3s. If I use up all of the SO2, I get 8 SO3s. The way that we interpret this is whichever reactant gives you the least amount of product, that reactant is the limiting reactant. All right, so in this case, we did a simple calculation involving stoichiometry to figure out that which 8 versus 6, which one is the smaller number? Obviously, 6 is a smaller number. Which reactant gave me the 6? It's the O2. So the O2 there is going to be the limiting reactant. All right, so in this question, we're looking at applying some of the same limiting reactant principles to stoichiometry. So it's solving moles to moles limiting reactant problems. And again, just like with the first couple of questions, having a balanced chemical equation is going to be your most important starting point. So it says methane, it gives you the formula gas and oxygen gas react to produce carbon dioxide gas and water vapor. So let's write that reaction. We have the formulas. So CH4 reacts with oxygen, O2, to form, so there's our arrow, carbon dioxide, CO2, and water vapor, H2O. That's your equation. We need to balance it. So if I do a quick balancing here, on the left side we have 1C, we have 1C on the right. On the left side we have 4 H's, on the right side we have 2 H's. So I need to make 4 H's on the right, so I'm going to put a 2 here in front of the H2O. 2 times 2 gives me 4 H's, but I've also not changed my oxygens. I have 2 O's plus another 2. That gives me 4 O's on the right. I need to put a 2 in front of the O2 to make 4 O's here on the left side. And I have my 1 in front of the CH4. That's your balanced equation. And a 1 in front of the CO2. So that's the first thing, which is usually the most challenging thing in questions like these. Write out and balance the chemical equation. Now it says, suppose you have 9.0 moles of CH4 and 1.0 moles of O2 in a reactor. Calculate the largest amount of CO2 that could be produced and round your answer to the nearest 0.1 moles. All right, so what we need to figure out here, we're going to do 2 sets of calculations. Starting with each of the reactants. Okay, and this is typically how your limiting reactants problems are going to work. You're going to start with each of the reactants and go through the stoichiometry to determine how much of the product we're going to get, right? And what we're trying to relate here is the amount of the CO2 that could be produced. So that's what we're trying to relate with each of the reactants. So let's take a look. We'll start with the CH4 first. Okay, so we have 9.0 moles of CH4, and now I want to relate the CH4 to the CO2. Okay, I'm going to relate the CH4 to the CO2. That relationship is a coefficient, which is a 1-to-1 mole ratio. So I can say 1 mole of CO2, I get that from the equation, is produced from 1 mole of CH4. Right, I don't really have to think too hard about that as long as my equation is balanced, moles cancel away, and obviously 9 times 1 would give me 9.0 moles of CO2. I'm going to do the same thing now, but I'm going to do it with the oxygen. So now I'm going to start with the O2. I have it says that we're starting off with 1.0 moles of O2. Now I'm trying to relate the O2 to the CO2. Okay, so that thing, that's a 2-to-1 mole ratio. So I can say 2 moles of O2 reacts to produce 1 mole of CO2. And you'll notice again, when I put my conversion factor in, I'm putting the unit that I want on top in the numerator, the other unit in the bottom, so that it can cancel out. So this then is going to give me 1 times 1 is 1 divided by 2. That's 0.5 moles of CO2. All right, so we've done 2 sets of calculations. We're going to compare these now. And whichever one is the least, the smaller number, that is going to be the maximum amount that I can make. Okay, so compare the amounts, and the smaller amount is the what's known as the theoretical yield, which is the maximum yield, or the maximum amount. So in this case, 0.5 moles is going to be the maximum amount of CO2 that we can produce. We can also say that what limits this reaction, what's going to be used up, is going to be the oxygen. All right, so in this case, or in this problem, looking at understanding the differences between theoretical, actual, and percent yield. And we're told a bunch of information about this drug, SLT88, that's made here. And the drug can be made by reacting together 2 compounds, A and B, which are very expensive. And they're trying to figure out different combinations to minimize the cost of making this particular drug. All right, so we have a couple trials here that are shown. Copy them over to the left side. I want to complete the table by calculating the theoretical yield and the percent yield of SLT88. We're going to round to the nearest milligram and percentage to the nearest whole percent. All right, so let's focus in on each of these trials so we can simplify our table. All right, so the first trial, we start off with 600 milligrams of A and 650 milligrams of B. And after we react them together, at the end, we have none of A left over, and we have 390 milligrams of B left over. All right, so we need to figure out, based on that, what the theoretical amount of SLT88 is going to be. So let's write in a basic equation that represents this reaction. So it says that this drug, SLT88, that we're trying to make, is made from combining A, whatever A is, together with B. All right, when we combine them, we end up with our drug here that we want, SLT88. So initially, we start off with 600 milligrams of A, plus we have 650 milligrams of B. And at the end, when I allow these to react and when the reaction is complete, I have none of A left over, and I have 390 milligrams of B left over. So what that means then is the amount of A that was used up, guess where it went? It went into making our SLT88. So the mass, or the amount of SLT88 that we make, would be that 600 milligrams plus whatever amount of B reacted with it. So how much of the B reacted? Did all of it react? Well, no. If all had reacted, there would be none left at the end. But there is some left at the end. So the amount of B that reacts would be the difference there, 650 minus 390. Right? That difference is how much of the B reacted with the A to make this particular drug. So this ends up being the 600 of A that reacted plus that difference in B. So 650 minus 390 would give 260. Okay, so if I add them together, I should get 860 milligrams of the drug here at the end. And again, I have none of A left over, and I have 390 of B left over. Now, if you think about this, This should make sense because in a chemical reaction, you cannot create or destroy matter. So the total mass at the beginning, at the start, right? At the start, all I have is just A and B. So these added together will give me 1,250 grams. Or milligrams, sorry. And at the end, guess how much I should have? I should also have 1,250. Well, at the end, this is what I have. When I add 860 to 390, that gives me 8 through 11, 1,250 milligrams at the end. All right, so that makes sense. You haven't created or destroyed stuff. The total amount at the beginning, A and B, is total amount left at the end. So the theoretical yield here is going to be, what did we decide? 860 milligrams of the drug that we should be able to get. Right, and if everything worked out perfectly, that's how much we should get. It's telling us though that the actual yield, when we actually do this experiment and we did it in the lab, we actually get 714 milligrams. And the theoretical amount, which we just calculated, was 860 milligrams. So the way that we determine the percentage yield is simply taking the actual amount, 714 milligrams, we divide it by the theoretical amount that we should get, 860, and then we times that by 100 because it's a percentage. Milligram goes away, 714 divided by 860 times 100 would be 83% yield. All right, so that, obviously you want to aim for 100% yield, you want to get everything you're supposed to, but in this case, we were supposed to get 860, but we only got 714 milligrams. So we're going to do the same thing for the second trial, figure out how much of the A and B react together to produce the theoretical yield of the product. We just divide the actual over the theoretical to give us, times by 100 would give us the percent here at the end. All right, so we got 860 and then 83, and do the same thing for trial number 2.